Assalamu alaikum. Welcome to the second lesson of the chapter Physical Optics, that is electromagnetic spectrum. In our last class, we started discussing electromagnetic spectrum, that is the range of frequencies of electromagnetic radiation, arranged either in the way of increasing frequency, that is from radio waves, microwaves, infrared, visible, ultraviolet, X-rays, gamma rays, or in the other way round, in the way of increasing wavelength. And we also discussed how, as a wave have more frequency, its wavelength will be less, and when a wave have less frequency, its frequency will be more. I also have seen some questions where they ask, like, which is the radiation which has a frequency of 10 raised to 16 hertz? Can you tell me which wave have frequency 10 raised to 16 hertz?
Ultraviolet.
Ultraviolet. So
Ultraviolet.
roughly you have to learn the numbers, frequency and wavelength for these waves. Radio waves together you can learn. No need to differentiate the radio waves, but you have to know the frequency range and the wavelength range for gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, and radio waves. Now, let us see how each of this radiation is produced and how they can be detected. So, here you can see a table where the different types of electromagnetic radiations are given, their wavelength ranges are given. What is meant by NM?
Nanometer.
Nanometer means 10 raised to how much meters?
10 raised to minus 9.
10 raised to minus 9. That is right. So, and millimeter, you know, it's 10 raised to minus 3. And here you have the frequency range of each of these radiations. Let us see how each one of them is produced. So radio waves are produced by the rapid acceleration and deceleration of electrons in areas. You must have seen above buildings areas that give out radiations or receive radiation. So these are called receivers areas, which are present to detect the radio waves. Radio waves also include the TV signals. So all broadcasting is done at the frequency range for radio waves, and they are produced with some areas and they are also received with another area. Then we have microwave. Where do we see microwaves in our daily use?
Oven.
Yeah, there are microwave ovens, right? So there is a magnetron wall inside each of the microwave oven that produce microwaves, and they can be detected using point contact diodes. It's a special kind of PN junction PN diode which have one single terminal. There will be a tungsten contact and you can detect microwaves using that, or even microwaves will be absorbed by water in food materials and they get heated up. So that is where we use microwaves in ovens, and they are also used for satellite communication. So magnetron wall or klystron wall is something which produces microwaves. Now, another kind of wave is infrared waves. And infrared waves are produced by vibration of atoms and molecules. What happens to a body when its atoms and molecules are vibrating at very high temperature? It will give away heat radiations, right? So when a body gets hot, even if you don't touch the body, if you place your hand near to it, you can feel heat, or you can feel heat radiations. It's mostly infrared radiations. So the vibration of atoms and molecules produce infrared radiation, because when we heat something, what happens? The atoms and molecules in that body starts vibrating. So when they vibrate, what happens? Infrared radiations, which are otherwise called heat radiations, will be produced. And these infrared radiations can be detected using thermopile, bolometer, or infrared photographic film. So there are infrared photographic films which is used to capture distant objects. For example, if we want to take the photograph of Earth from moon, we can use infrared radiations, because see, they have a higher wavelength than light. So they can travel for a longer distance without getting scattered. And thermopile is a device that converts the thermal energy to electrical energy. So infrared radiations means thermal radiations. It can be detected. Do you know what are the radiations which we get from sun? Out of these, which are the radiations that we
Ultraviolet.
ultraviolet? Then what? From sun,
Light.
light, and also it's very hot when we walk outside.
Infrared way.
Infrared. So these three electromagnetic radiations, infrared, light, and ultraviolet, are the radiations which we obtain from sun. So the heat energy is mostly due to the infrared radiations from sun. And then another kind of electromagnetic radiation, which is more common, that is light, is produced by electrons in atoms when they move from one energy level to lower energy level. We know that the atom contains electrons and they are moving in orbits, and each orbit have a different energy level. So when an electron jumps from a higher energy level to a lower energy level, the difference in their energy level is given out in the form of light. And this light can be detected with our naked eyes. Out of all this electromagnetic radiation, only light is visible to us. The rest of the electromagnetic radiations cannot be detected by human eye. And then there are photocells. Do you know what is photocells?
Cells of photons.
Yeah, when photons or light is incident on something, electrical energy is produced. So they are called photocells. So photocells and also photographic film. That is the usual films which we use for photography. So these are the things which can detect light. Then ultraviolet rays are produced when inner shell electrons in atoms move from one energy level to a lower energy level. See, the light has lesser frequency than ultraviolet rays. Means light energy is less compared to the energy of ultraviolet rays. Higher the frequency, higher the energy. So the electrons in the inner shells of atoms are bound close to the nucleus, and the distance between the shells are more, or the energy difference between the shells are more as you go to inner shells. When we go to the outer shells of electrons in an atom, they are more closely spaced in terms of energy. So the energy difference between one level and another level is not much when we go to the higher energy levels or outer energy levels. But as you go to the inner shells of electrons in an atom, the energy difference is more. So if an electron jumps from an inner shell to a still lower level, what happens? The energy difference comes out as ultraviolet rays, because there the energy and the frequency is more than when an electron jumps from a outer energy level to a lower energy level. So here in both,
Teacher,
yes,
lower energy level means it's close to the nucleus.
yes, closer to the nucleus.
Okay.
And then closer to the nucleus, and the value of energy also will be less. As the electron go to higher energy level, they are further away from the nucleus and they are closely spaced. Then ultraviolet rays are also detected by photocells. Photocells means the devices that converts electromagnetic radiation to electrical energy. They are also detected by photographic film. And then X-rays. X-rays are produced by X-ray tubes or inner shell electrons, still inner ones. So X-ray tubes are found in hospitals. X-rays are taken in hospitals, right? So they are produced in X-ray tubes, and they are also detected by photographic film, and Giger tubes are special tubes which detect the presence of X-rays. Then you have gamma rays. Gamma rays are emitted by radioactive decay of the nucleus. See, as we go down, as we go to higher frequency, as we go to higher energy of electromagnetic radiations, they are emitted by innermost parts of atoms. See here, infrared by vibration of atoms and molecules as a whole. When we get to light, emission of light is by the jumping of electron from one energy level to lower energy level. It may not be due to the innermost shells. See, ultraviolet, it comes to innermost shells, more nearer to the nucleus. X-rays means still inner shells. And gamma rays, see, from the nucleus. So it's going deeper and deeper into the nucleus. So gamma rays are emitted during radioactive decay of the nucleus. Have you learned radioactivity before in lower classes?
Yeah, we learned
What
to
are the
get the
three
idea
kinds
only.
of radiations emitted? You call them?
Um,
Do you remember?
which one, teacher?
Alpha, beta, and gamma
Gamma.
radiations are emitted, right? So these are the gamma rays. Alpha rays are positive, beta rays are negative, and gamma rays are neutral. They are not charged. They are electromagnetic radiations of very high energy. See, very high frequency means very high energy. And they are also detected by photographic film. And we can also detect the presence of gamma rays using ionization chamber. As I told, they are high energy electromagnetic radiations. So when they pass through air, they ionize the atoms in their path. So that can be detected in an ionization chamber. So I think this is clear to you. Different types of electromagnetic radiations, and just go through all the production mechanisms and how they are detected. This may come for your multiple choice type of questions. Is it clear to you?
Yes,
Yes,
teacher.
teacher.
Okay, so let me go to the next one. That is some of the uses of electromagnetic radiations. Radio waves, as we told before, it is used for broadcasting and communication. And this is because they have very long wavelength, and therefore they can travel a far distance in the Earth's atmosphere without being scattered much. And they are not much, even if they gets reflected off hills, they can still travel a long way through the upper atmosphere. Therefore they are used as radio waves. They are used for broadcasting and communication. Now another kind of wave is microwaves. As you know, it's used for cooking food. Microwaves are absorbed by water molecules, causing them to vibrate. So when these molecules of water vibrate, the faster they vibrate, the hotter they become. You have learned in grade 11, last chapter, that the temperature, absolute temperature, is directly proportional to the kinetic energy, right? Average kinetic energy. So as they vibrate more, they become hotter, and it's used for cooking food. Now, it is also used for satellite transmissions. Their wavelength penetrates our atmosphere, so they can go beyond our atmosphere because of comparatively large wavelength. Then another one is infrared rays. Infrared rays are also called heat rays, and it is possible for night vision equipment to detect infrared rays. Have you seen pictures of people whose temperatures are taken?
Warm that machine which is
Yeah, yeah.
like that. Yeah,
Yeah,
we saw red something like.
yeah. It shows red, right? More red means there
Yeah,
are more heat energy radiated from that body. So if it is too much red, it means more heat energy is radiated. So from a distance, the temperature of the persons are detected because hot bodies emit infrared radiation. So, infrared radiation detectors are actually used to detect the temperature of body of objects or even animals or human beings at a distance. So, heater and night vision equipments use infrared, and all objects, including people, give out infrared radiations which can be detected even at night. So, higher the temperature, more the infrared radiations emitted. It's also used for television remote controls. So, when you use remote controls at home, it contains infrared radiations. That's why you can communicate with your TV at a distance. So, when you press the remote controls, what radiation is going and detected by the TV? It's infrared. And then we have visible light. You know the uses of visible light. What are they? You know, visible light is used for what? For seeing objects, for human vision. And it is also used for photography and even in optical fibers. And it's the only part of the spectrum we can see. Then we have ultraviolet rays. Ultraviolet rays are used in fluorescent lamps. What is fluorescent lamp? They have chemicals inside them which absorb ultraviolet rays and convert the energy to visible light. Have you seen certain balls which, if you hold for some time in daylight and if you go to a dark place, still it shines? Have you seen such things?
glowing.
Yeah, glowing.
Yeah,
They are
Magic.
fluorescent. So when you take
yeah.
it out to the sun, what happens? It will absorb the ultraviolet. And after some time, it will convert that ultraviolet to visible light and give it out. So you can see it glowing. So, ultraviolet rays are used in fluorescent lamps, and also X-rays. X-rays, you know, it's used in medical equipment to diagnose. So, X-rays will pass through our body, but it will not pass through into our bone much. So, you can get the X-ray images of bone. So, when if there are any fracture, you can identify that. So X-rays are used in medical equipment. They enable us to see the internal structure of objects and materials by passing through some substances like body, but being absorbed by others. For example, bone. Bones absorb the X-rays while it can pass through the human body tissues, other flesh and all. Then we have gamma rays. Now, gamma rays are used for sterilizing food. because gamma rays, as I told before, are dangerous. They can kill cells, living cells. So if food items have some bacteria or something, living cells which are not good for us, a gamma rays are used to sterilize the equipment, food and medical equipment. They are highly penetrative and can kill living cells. So it is dangerous to being exposed to gamma rays. There is one more region where gamma rays are used to kill living cells, but for a medical purpose. Do you know?
For cancer or tumor?
Yes, exactly. For cancer and tumor, there are undesired cells in our body. A cancer patient will have undesired living cells. So those cells are killed using gamma rays. So through radiation therapy, tumors and cancers are cured. So these are some of the uses of electromagnetic radiation. Now, one question, you all know the speed of these electromagnetic radiations through vacuum. How much is that?
Same like light, right?
Yeah,
3 into 10 raised to 8
meter per second.
meters per
So
second.
in 1 second, how much distance will uh, infrared ray travel in 1 second?
3 into 10, 3 into 10 raised to 8 meter.
Yes, it will travel for a distance of 3 into 10 raised to 8 meter. Now, how much distance will light ray travel in 1 minute?
Into 60.
Yes. How much distance will it travel in 1 hour?
Again into 60.
In 1 day?
Into 24.
In 1 week?
Into 7.
Okay. In 1 month?
30.
Into what? No, no, it's
In
going
one
from week
month?
to month.
So
Into
it depends
30.
upon the number of days in a month.
Yeah,
You have to multiply with 30 or 31, right? What about in
yeah.
1 year?
Then it's
360.
12. If
300
it's
and
days,
okay, if you know the months, you just have to multiply with 12. But every month have different number of days, right? So you will
yeah,
have to
360.
multiply after 24 into
5.
365.25, because there is leap year. Every fourth year, one additional day comes, right? So with this concept, we have a new quantity which is called light year.
Light.
Light year. What is light year?
The distance.
Yeah, it's the unit of distance. See, when you hear this year, you have a tendency to feel that it's a unit of time. No, light year is the unit of distance. So let us see what is light year. A light year is the distance light travels in 1 year. Okay, so the total distance traveled by light in 1 year is called a light year. So how much is that? It is 3.5 trillion kilometers. What is meant by trillion? How much is 1 trillion?
1000 billion
Yeah,
equal
you
to
are
1
right.
trillion.
10 raised to how much?
Oh, that I don't know. Maybe 12.
Yes, 10 raised to 12. So the distance light travels in a year is 9.5 into 10 raised to 12 kilometers. Kilometer is not the SI unit. You have to convert it to meters. So again multiplied by 10 raised to 3. So much distance is traveled by light in 1 year. So a light year is a unit of distance, not time. Light travels at 186,000 miles per second. So you know this value, 3.0 into 10 raised to 8 meter per second. And the light year is the distance that light can travel in a year. And how you will get it? You will have to multiply the speed of light times 60. So many it means 365 days times 24 hours times 24 minutes times sorry times 60 minutes times 60 seconds into velocity of light will give you the total distance, which is 1 light year. So you can remember 1 light is equal to 9.5 into 10 raised to 12 kilometers, or 9.5 trillion kilometer. That is the distance traveled by light in 1 year. Okay. Now, this unit of light is usually used when we say the distance between Earth and other uh, distant stars, or the distance between Earth and other planets, like that. See, we are part of a solar system, right? Earth is part of a solar system. You know that. Now, the solar system is part of a big galaxy called Milky Way galaxy, which contains the Earth solar system. And it is about 100,000 light years in diameter. Okay. So suppose we are on Earth and we are observing a star which is far away in our galaxy, maybe at the end of our galaxy. So when you look at the star, do you think what you see is the star that exists there now? Suppose at night you are going out and looking at a star. You see a star, right? Do you think the star you see there exists there then? No.
So what?
Suppose you go at night, when you look at the sky, you see a star, right? You see stars.
Yes.
Yeah.
Now, when you look at it, you feel that the star is there now. You are seeing the actual star which is
Yes.
present there now. But actually, you are seeing a star which was present there some 50 or 100,000 years before. Not the star which is there now. Why?
That means if it is destroyed, then also the light will be coming, right?
Yeah, because that light takes
Still
100,000
come.
years to reach our eyes, right?
Oh shit.
So when you are looking at a star, observing a star, what you are seeing is what existed there many years before. Because light takes so many years to travel that distance between the earth and star.
Teacher, that means we can see past, right?
What you can see?
Like if an alien is there in, I mean, it's very distant from us, so they will see the dinosaurs.
There is a chance if they can, if there are many, maybe thousands of light years away, if there is another universe, or if there is another planet similar to earth where there are living beings, and if they watch from there, maybe they can see what existed on earth 100,000 years before.
Yeah.
Definitely, they will
That means
need
teacher.
high resolution. That's good thinking.
That means if we go to the planet before the light, then we can see the past, right?
How can we travel faster than
No,
light?
I'm just saying, like if we
Yeah,
travel.
if you can travel faster than light, what happens is you can do time reversal. You can travel to future.
But the teacher, how future? I mean, it doesn't happen, right? Then how can we see the future? The past can be seen because the light is still going to some other planets, right? Then if
Yeah,
we
but
go
where
into
by
that,
the time they see that, it would be past.
oh, it's so confusing.
So, so that is why theoretically as well, the whole physics theory is based on the concept that light is the fastest moving thing possible. So if we find anything which can travel faster than light, which can travel faster than electromagnetic radiation, we will have to uh, change the whole theory of physics. There will be a lot of changes required. So many theories in physics are based on this concept that light is the fastest thing, or electromagnetic radiations traveling in vacuum are the fastest. So I hope the concept of light year is clear to you. So light year is a
Yes,
unit
teacher.
of
Distance.
distance, and 1 light year is equal to, how will you convert that to meters? How will you convert light year into meters? 1 light year is equal to 9.5 times 10 raised to 12 times 10 raised to 3 meters. So here the next nearest star, see, nearest star to Earth is Proxima Centauri. It is about 4.2 light years from Earth. So when you are looking at the nearest
9.5
star,
trillion
what you are
kilometer.
seeing is what existed there 4.2 years before. So let us go to another concept, new concept, which is called wavefront. Tomorrow, we will be discussing the wave theory of Christian Huygens. But before going to the wave theory of Christian Huygens, we need to know what is a wave and what is a wavefront. I hope you already know what is a wave. What is a wave? Any kind of wave. A wave is a periodic disturbance that displaces energy from one place to another in a material medium, but do not displace the particle of the medium. For example, here you can see ripples of water. There is a small disturbance here, and what happens? A wave is produced. So the disturbance or the energy is transmitted from this point through these ripples to the outside. See these circles, it will go. Suppose if we keep a piece of paper here on the ripple, how will that piece of paper move? Will it move outwards or will it move up and down? What will happen to a piece of paper which is kept here? You have no idea? Try it at home. The piece of paper will not move outwards. The piece of paper will move just up and down, which means when there is a wave, there will be a disturbance, and the disturbance or the energy will move outwards. But the particles which are carrying this disturbance will not move along with the wave, they will just oscillate up and down. That is the meaning of saying the periodic disturbance that displaces energy from one place to another, but do not displace the particle of the medium, is called wave. So this is wave. This is an example for water wave. This is an example where the light wave from a candle is moving outside. And all these are waves. Now, the locus of all the particles at the same phase on a wave is called the wave front. So as the light propagates out, here you can see circles, right? When you take this circle, all the water molecules here are moving up, which means they are in the same phase. Now, when I take another place here, here all the particles are moving down, which means they are in phase. So all these circles are locus or path of the particles of the same phase. So this locus is called a wavefront. So these are circular wavefronts. Okay, so on the surface of water, the shape of the wavefront is circular. Now it's about to finish, the time is about to finish. We will see more about wavefront and we will deal with wave theory put forward by Kristen Huygens in our next class.